Welcome, Leetcoders! It's your boy Diego. Today we're going to be solving the problem known as the odd-even linked list problem. Remember, you can pause or rewind this video at any time if you'd like to take a closer look at what is going on.
Problem description.
This problem has a challenge level of medium. Okay, let's take a look at the problem description. Given the head of a singly linked list, group all the nodes with odd indices together, followed by the nodes with even indices, and return the reordered list. So the first node is considered odd, the second node is considered even, and so on. Note that the relative order inside both the even and odd groups should remain as it was in the input. You must solve the problem in order of 1, extra space complexity, and order of n, time complexity.
Pitfall.
Beware of this pitfall for this problem. Many computer indices start with a first index at 0. The first index for this problem starts at 1.
Concept review.
Let's take a look at the concept review of a singly linked list. The singly linked list is a linear data structure in which each element of the list contains a pointer which points to the next element in the list. Each element in the singly linked list is called a node. Each node has two components, a data component and a pointer component which points to the next node in the list. The first node of the list is called the head, and the last node of the list is called the tail. The last node of the list contains a pointer to null. Each node in the list can be accessed linearly by traversing through the list from head to tail.
Conceptual overview.
Okay, let's take a look at the conceptual overview. Here we see in example 1, we are given a singly linked list. Represented in this image is a series of circles representing the nodes of our list. The arrows represent pointers to the next node in the list. Now this large white arrow in the middle represents the processing of your code. Then the second row of circles represents the output of your code. The nodes with odd indices in the given list are shaded with a light gray background. And the nodes with the even indices in the given list are shaded with a dark gray background. We can also see the values of each node represented as integers. Also shown is a textual representation of the singly linked list, with the input list and output list, which mirrors the values in the illustration. The first index has a value of 1, the second index has a value of 2, the third index has a value of 3, and so on. For this example, it is just a coincidence that the values of each node match the index for each node. Now the solution must return the nodes with odd indices together, followed by the nodes with even indices together. And in the second row of circles, we see the reordered list, which should be singly linked list result returned by your code, with the first node value coming from the first odd index of the given list with a value of 1. Then the second node value comes from the second odd index of the given list with a value of 3. The third node value comes from the third and last odd index of the given list with a value of 5. And that concludes the grouping of the odd indices from the given list. Then the next node starts with the even indices from the given list. So the fourth node value comes from the first even index of the given list with a value of 2. And the fifth node comes from the second and last even index of the given list with a value of 4. And that concludes example 1.
Pitfall.
Beware of this pitfall. This problem is not grouping odd and even node values. This problem is grouping odd and even node indices. Let's look at example 2. Here again, we see a graphical representation of our singly linked list and a textual representation. The graphical representation has odd node indices shaded in light gray and even node indices shaded in dark gray. In this, example 2, we see that we are given a singly linked list with the values 2, 1, 3, 5, 6, 4, 7. This time the node values do not match with the node indices, so we must really pay attention to the odd and even indices. So how would this translate into the resulting singly linked list? First, we would group the values with the odd indices, namely index 1, index 3, index 5, and so on, resulting in a singly linked list with values 2, 3, 6, and 7. And that would conclude the grouping of the odd indices from the given list. Finally, we group the values of the even indices, namely index 2, index 4, index 6, and so on, resulting in part 2 of the singly linked list with the values of 1, 5, and 4.
Constraints.
The constraints for this problem are: the number of nodes in the linked list is in the range of 0 to 10 to the 4th, also known as 10,000, and node.val, or node value, could be a value falling between negative 10 to the 6th, also known as negative 1 million, and 10 to the 6th, also known as positive 1 million.
Solution walkthrough.
Solution intuition. Put the odd nodes in a linked list and the even nodes in another. Then link the even list to the tail of the odd list. Solution algorithm. The solution is very intuitive, but it is not trivial to write a concise and bug-free code. A well-formed linked list needs 2 pointers, head and tail, to support operations at both ends. The variables head and odd are the head pointer and tail pointer of one linked list we call odd list. The variables even head and even are the head pointer and tail pointer of another linked list we call even list. The algorithm traverses the original linked list and puts the odd nodes into the odd list and the even nodes into the even list. To traverse a linked list, we need at least one pointer as an iterator for the current node. But here, the pointers odd and even not only serve as the tail pointers, but also act as the iterators of the original list. The best way of solving any linked list problem is to visualize it either in your mind or on a piece of paper. An illustration of our algorithm is following.
Code walkthrough.
Okay, let's look at the code walkthrough. The code in this video will be Java code. Here we will see a side-by-side view of the solution code and a singly linked list structure diagram. On line 1 of our solution code, we declare a public class named solution and begin our code block with an open curly brace. On line 2, we declare a public function odd-even-list of data type listNode that accepts an argument head of data type listNode. Then we open the code block for this function with an open curly brace. In line 3, we do some housekeeping. If the input parameter head is equal to null, then return null. None of the examples passed in an empty list, but it could be possible, so we want to be able to handle that case if it arises. Note that all Java statements in our code are terminated by semicolons. Now let's look at step 0 of our diagram. In line 4, we see a number of things happening. First, we initialize a list node odd and point it at the list node head with the assignment operator. Then we initialize a list node even and point it to the list node that is the next node after head, accessed by head.next. Finally, we initialize a list node even head and assign it to point to the list node even. Remember, you can pause or rewind this video at any time if you'd like to take a closer look at what is going on. We're going to move on to step 1 in our diagram, and now let's look at line 5 in our code. Note that all the node data types in this code are called list node, but I'm going to just start calling them nodes. Line 5 sets up a while loop that will traverse the given singly linked list. While the node even is not equal to null, and while the node at even.next is not equal to null, run the code block of the while loop. Then we have an open curly brace to open the code block for this while loop. If we take a look at the diagram, we see that the node even is closer to the tail of the list than the node odd is. In fact, the node even will always be closer to the end of the tail list than the node odd will be as we traverse the list. So all we need to do is check when the node even has reached the end of the list to know when to terminate the while loop. Note that the node head is not manipulated as part of the while loop and will always point to the head of the odd indexed nodes. In fact, we don't even have a node named odd head as we do with even head because the node head will serve that role. On line 6, we point to the node at odd.next, to the node at even.next, which effectively skips over the nodes with even indices. On line 7, we point the node odd to odd.next, which traverses the odd node through the list. On line 8, we point the node at even.next to the node at odd.next, which effectively skips over the nodes with odd indices. On line 9, we point the node even to even.next, which traverses the even node through the list. On line 10, we close the code block for the while loop with a closed curly brace. Now, let's take a look at what we've created with our while loop by looking at the figure. We can see in the figure that we now have two separate singly linked lists. First is a singly linked list of odd indices with the node head pointing at the head and the node odd pointing at the tail. Second is a singly linked list of even indices with the node even head pointing at the head. And the node even is pointing at null, which is a condition to exit the while loop. Also note that in this figure, it is a coincidence that the node values and index values were the same. The node values can be any value, and we are only looking at the oddness or evenness of the indices as mentioned in the pitfall. In line 11, we can see the final step in our figure. The node at odd.next, which was at the tail of the odd index list, is assigned to point to even head, which is at the head of the even index list, thus completing our reordering and creating the final singly linked list. Line 12 returns the node head, which points to our resulting list. Line 13 closes the code block for odd even list with a closed curly brace. And line 14 closes the code block for solution with a closed curly brace.
Complexity analysis.
Looking at the complexity analysis for this problem, we see a time complexity of order of n. There are a total of n nodes, and we visit each node once. And a space complexity of order of 1. All we need is the 4 pointers. And there you have it. That was the problem and solution for the odd-even linked list problem. Thank you for being a part of Leetcode.